Right now, you live in the most frictionless era of human existence. If you want a pair of shoes made in Vietnam, you tap a screen and 3 days later, they're sitting on your porch. You want fresh coffee beans grown on the side of a volcano in Ethiopia? You buy them at the corner store for less than the price of a movie ticket. You don't think about it. I don't think about it. To us, the world is just one giant, instant vending machine. But here's the reality. Almost nothing in your room actually originated anywhere near your house. Take this shirt you're wearing right now. The raw cotton was likely harvested in Texas, thrown onto a vessel to be spun in Vietnam, shipped to Bangladesh to be stitched together, and then sent back across the ocean to sit on a hanger in your local store. And somehow, after traveling thousands of miles across open ocean, that shirt still only cost you $15. How is that even mathematically possible? Because over 80% of everything on this planet, your phone, your furniture, your food, your car parts, spent weeks locked inside a giant metal box floating in the middle of the ocean. You are looking at the invisible engine of the global economy. We like to think the modern world runs on silicon, software, and cloud servers. It doesn't. It runs on steel, diesel, and heavy ocean hydraulics. If this single system paused for just 3 days, grocery store shelves would start going bare. Within a week, car factories in Germany and tech plants in Taiwan would grind to a dead halt. Within 2 weeks, the global financial system would enter a tailspin. This isn't just about big boats carrying freight. In this video, we are dissecting the greatest economic hack in human history, how a humble, rust-stained 20-foot box restructured global geopolitics, slashed the cost of living for billions of people, and created a hyper-efficient machine that is terrifyingly fragile. To understand how we built this monster, we first have to look at the absolute nightmare that existed before it. If you traveled back in time to 1950 and looked at a commercial port, it didn't look like a high-tech logistics center. It looked like an absolute madhouse. Back then, shipping operated on what was called break bulk cargo. That meant every single item was loaded individually. You'd have sacks of coffee stacked next to wooden crates of whiskey, tied down next to steel pipes and bundles of lumber. Imagine playing a high-stakes game of Tetris, except every single block is a completely different shape, weighs half a ton, is made of splintering wood, and you have to load it by hand in the pouring rain. This created a massive bottleneck. A cargo ship would spend more time sitting docked at a harbor being loaded and unloaded than it actually spent sailing across the sea. In fact, ships routinely spent over 50% of their operational lives stuck in port. And that sitting time was ridiculously expensive. Loading a ship in the mid-1950s cost roughly $5.86 per ton in labor alone. In today's money, that's equivalent to over $65 a ton just to get goods onto the vessel. Add in rampant dockside theft, damaged goods from clumsy handling, and rotting food, and ocean freight was so slow and expensive that most companies simply didn't trade internationally unless they absolutely had to. The guy who fixed this wasn't a veteran sea captain. He wasn't an admiral, and he wasn't a naval architect. He was a truck driver from North Carolina named Malcolm McLean. Back in 1937, McLean was sitting in his truck at a port in New Jersey, waiting hours, sometimes days, just to hand off his cotton bales to the dockworkers so they could unpack his truck and pack the ship. Sitting there frustrated, he had a crazy thought. Why are we wasting days moving individual items out of the truck and into the ship? Why don't we just pick up the entire truck bed, drop it onto the ship, and haul the whole thing? It took him nearly 20 years to raise the money and buy his own ships, but on April 26, 1956, McLean put his radical idea to the test. He loaded 58 standard corrugated steel boxes onto a converted World War II oil tanker named the Ideal X and sailed from Newark to Houston. The results blew the entire industry out of the water. McLean managed to drop the loading cost from $5.86 per ton down to just 16 cents per ton. That wasn't a 10% improvement or a 20% improvement. That was a 97% price drop overnight. This birthed intermodal transport. The cargo inside the box never had to be touched by human hands between the factory floor in Asia and the warehouse in America. Truck, train, ship, truck, all using the exact same locking mechanism. Once the world agreed on standard dimensions, the standard 20-foot and 40-foot containers we see today, the cost of moving goods around the globe collapsed. And once shipping became practically free, global manufacturing exploded. But to keep up with this new world, engineers had to build ships on a scale that defies physics. Once the world realized metal boxes were the cheat code to global wealth, a new engineering war started. How big can we make these ships before physics says no? Welcome to the era of the ultra-large container vessel, or ULCV. To give you an idea of what we're dealing with today, ships like the MSC Irina can carry over 24,000 TEUs. TEU stands for 20-foot equivalent unit, basically one standard container. 24,000 of them. That number is so massive it's hard for the human brain to process, so let's scale it down. A modern megaship is roughly 400 meters long. That's longer than the Eiffel Tower is tall, and wider than an American football field. If you took all 24,000 containers off a single one of these ships, stacked them end to end on a flat track, you'd have a freight train stretching over 90 miles long. That is a single ship's worth of cargo. And to push a steel city weighing 220,000 tons through heavy ocean saltwater, you can't use a normal engine. You need something like the Wärtsilä RTA 96C, a two-stroke turbocharged diesel engine that stands 44 feet tall, weighs 2,300 tons, and cranks out over 100,000 horsepower. The crankshaft alone weighs more than 300 elephants. Now think about this for a second. How do you stack thousands of metal boxes 10 stories high on top of a floating vessel, hit a 40-foot ocean wave, and not watch the whole thing tumble into the ocean like a tower of Jenga blocks? The secret lies in engineering you never see from the outside. First, deep inside the ship's hull are cell guides, essentially giant vertical steel tracks. When cranes drop a container into the ship, it slides down these tracks like bread into a toaster, locked into place with millimeter precision. Second, there's the balance game. An automated system constantly measures the ship's tilt, instantly pumping thousands of gallons of seawater between internal ballast tanks to keep the deck perfectly flat. And then there's fluid dynamics. Notice that weird, giant nose sticking out under the water at the front of the ship? That's called a bulbous bow. It alters the way water flows around the hull, reducing wave resistance and cutting fuel usage by up to 15%. And fuel is everything here. In fact, these ships practice something called slow steaming. By dropping their speed from 24 knots down to 18 knots, they cut their engine's fuel consumption by nearly 50% because water drag scales exponentially with speed. But building a ship this massive creates a completely new problem. What happens when it reaches the shore? If a megaship is sitting idle at a dock, it isn't making money. It's burning tens of thousands of dollars a day in port fees, fuel, and crew costs. Which means when a vessel carrying 24,000 containers rolls into a port like Rotterdam or Shanghai, there is no time to waste. Unloading that ship isn't a job for humans with forklifts anymore. It is a hyper-synchronized, fully automated ballet. It starts with the ship-to-shore cranes structures as tall as 30-story skyscrapers. Operated by precise algorithms and high-definition cameras, these cranes drop down a heavy steel frame called a spreader bar. It locks onto the top four corners of a 30-ton box in a fraction of a second, lifts it hundreds of feet into the air, and drops it onto the dock with millimeter precision. Waiting below are HVs, automated guided vehicles. These are electric, driverless platforms that run 24/7 in total darkness. They navigate using thousands of transponders embedded under the asphalt, calculating the most efficient path through the maze without ever hitting each other. The HV carries the box deeper into the yard, where automated stacking cranes scoop it up and slot it into a hyperdense grid, organized by a central computer that already knows the exact destination, weight, and departure time of every single item. This whole process happens continuously, day and night, rain or shine. In a top-tier automated port, crane operators sitting in air-conditioned control rooms miles away oversee 4 or 5 cranes at once using joysticks and monitors. What used to take an army of longshoremen 3 weeks of backbreaking manual labor in the 1950s now takes less than 24 hours. It is the most efficient logistical engine ever designed by human beings. But because we pushed this system for maximum efficiency and zero extra slack, we accidentally made it terrifyingly fragile. We spent 6 decades perfecting this machine, making it bigger, faster, and cheaper. But in our quest for extreme efficiency, we eliminated all the slack in the system. We created a just-in-time global economy where nobody keeps extra inventory in warehouses anymore, because the ocean is the warehouse. And that entire multi-trillion-dollar web relies on a few impossibly narrow geographical needles that we have to thread every single day. Take the Suez Canal in Egypt, a ditch of water barely 200 meters wide connecting Asia to Europe. In March 2021, one single 400-meter megaship, the Ever Given, got caught in a sandstorm, wedged itself sideways, and lodged into both banks of the canal. For 6 days, the world watched in real time as a $200 billion vessel got stuck like a couch wedged in a narrow hallway. That one single incident held hostage an estimated $9.6 billion worth of global trade every single day, roughly $400 million an hour. Hundreds of ships were stranded in a massive maritime traffic jam visible from space, causing supply chain ripples, factory shutdowns, and price spikes that lasted for over a year. And Suez isn't unique. Whether it's severe droughts dropping water levels in the Panama Canal, tension in the Strait of Taiwan, or security crises in the Red Sea forcing ships to bypass Africa entirely and add 2 weeks of transit time. The global economy is constantly one bad day away from a systemic heart attack. Then there's the elephant in the room, the environmental cost of moving the world. These massive vessels run on heavy fuel oil, also known as bunker fuel. It's essentially the sludge left over at the bottom of the oil refining process. It's cheap, thick as asphalt, and burns extremely dirty. Collectively, global shipping produces roughly 2.5 to 3% of all global greenhouse gas emissions. If maritime shipping were a country, it would be the 6th largest polluter on Earth, emitting more CO2 than Germany. But here is the ultimate paradox of modern logistics. Shipping is simultaneously one of the world's biggest polluters and the most carbon-efficient form of transport ever created per unit of cargo. Moving a single container full of iPhones from Shanghai to Los Angeles creates less CO2 per item than a local delivery van driving those same phones 50 miles from a warehouse to your local store. That's why the industry isn't shrinking, it's reinventing itself. Right now, maritime giants are spending billions racing towards zero-carbon fleets, building vessels powered by green methanol, liquid ammonia, and even installing 130-foot automated wind sails to pull these 200,000-ton behemoths across the sea. The invisible machine is changing faster than ever because if it stops evolving, everything else stops with it. It's easy to look at a 20-foot steel box and just see rust, grease, and cheap metal. It isn't sleek like an iPhone. It isn't glamorous like a supercar. But when you step back and look at the whole picture, that simple metal box is arguably the most influential object of the modern era. It broke down geographic borders, transformed global labor, lifted hundreds of millions of people out of absolute poverty through global trade, and made the modern standard of living possible for billions. So the next time you tap a button on your phone, sip a cup of imported coffee, or put on a pair of sneakers, take a second to think about the journey it took to get to you. It didn't just appear out of thin air. It traveled thousands of miles across open oceans, survived 40-foot waves, threaded through narrow desert canals, and danced through a fully automated robotic maze, all tucked safely inside a corrugated steel shell. The container ship isn't just a big boat carrying cargo. It is the invisible machine that holds our world together. If this video changed the way you look at the everyday items around you, hit that like button, subscribe to the channel, and drop a comment below telling me where you think the shirt you're wearing right now traveled from. Thanks for watching, and I'll see you in the next one.